Okay, quick take on some 3233 stuff. Wanted to talk to you about, well, first off, reminding about synthetic division. Quick take on that is, remember, if this is an x plus 2, we're going to put a minus 2 instead of a positive 2 to take care of that sign switch ahead of time so we don't have to deal with the minuses later on. And then all of this, we're going to keep the coefficients as all. So then remember, with the x to the 3, there's no number there, so we'll put a 1 basically. So it's a 1, 9, 16, 11. Here we go. We'll do that too. 1, 9, 16, 11. 1, 9, 16, 11. Then we'll just get rid of the old times and plus, except remember, if that starts with a 1, so do we start with a 1. Our answer will start with a 1 as well. So then they start 1, we start 1. Beyond that, we're going to say everything gets times by negative 2. Here we go. Negative 2 times that 1 is negative 2. Then we'll add that down, and then the new answer will times by negative 2. So let's add that down. 9 plus negative 2 is 7. We'll times that with the negative 2. Negative 2 times 7 is negative 14. Let's add that down, and then that will times with negative 2. So 16 and negative 14 is 2, I guess. Then negative 2 times 2 is negative 4. And then finally, 11 plus negative 4 is 7. Giddy up. Now we have to interpret that answer, of course. So then remember what that looks like is we started with x to the 3 something, divided out an x basically. So if we have an x3 deal, divide out an x, that's like taking, it's like x3, divide out an x, you cancel the x, you got 2 of them left. And so we'll say our answer is going to be like x3 divided by x. We'll be looking at x2 here, it looks like. And so this first term that we got is 1x2, or squared or whatever, and then plus 7x, and then plus 2, no x at all. That's all the stuff. And then since this isn't a 0, we just have a non-zero remainder. That's our remainder. So we have a quotient there of x squared plus 7x plus 2. You could put the 1 on it if you like. And then a remainder of 7. Sometimes we'll be putting that in fraction form and stuff. For right now, just 7 is good. Cool. What else? Let's see. This will be interesting. Check this out. So number 7 and 8 here. Okay. Number 7, polynomial degree 5. And they call it p of x. It's just a polynomial function thing. It has a leading coefficient of 1. It has roots, multiplicity 2 at x equals 2, and x equals 0. And then a root of multiplicity 1 at x equals negative 2. And they don't really say anything beyond that. And so remember what this means is, first off, if they say polynomial degree 5, that means this is up to x to the 5th power is what we're looking at. There's essentially x5 somewhere in here is how much x we got going on. If we're to be constructing this from zeros and roots or whatever, essentially what we'll be looking at is something like this polynomial p of x here will be equal to something like 5 factors maybe. 4, 5 of them, each with an x in it, x plus this, x plus that, x minus this, so that by the time I times them all out, it's x something times x times x times x times x. That's 5 of them, which would be x to the 5 or degree 5. And so this putting out in our linear factors, and we just got to know what they're trying to say when they say all this weird stuff about multiplicity and roots. And so here's my take on what they mean. It has a leading coefficient of 1. That's easy enough. That means there's no number next to the x squared term or x to the 5th term. Sometimes you'll see these things even after we're FOILed out or something like that, and you have an x to the 5, and it'll be like there's a 3 with it, and sometimes there ain't no number. And so if they say leading coefficient of 1, that just means we don't have a number next to it in front, even whether or not we FOIL this all out. So we won't have to worry about there being a number in front of there, and that's nice. But then beyond that, what they mean by all of this stuff is it has roots of multiplicity 2 at x equals 2 and x equals 0. So let's talk a bit at a time here. When we have a root at x equals 2, we'll talk about the multiplicity thing in a second, but when we have a root at x equals 2 or at x equals 0, what that means is, to say root is x equals 2, is that essentially 2 is a 0 of our function, or you would say even an x-intercept of the graph. And so what that might look like to us is we're going to say 2 is essentially a number that I can plug in to my function that will make this thing all equal 0. And so a quick way to take that is we say, well, what if I did x minus 2? If I do x minus 2, then that means that positive 2 that they're talking about, if I plugged it into this, then 2, that positive 2 they're just mentioning, take away 2, would make 0. And so we just have to come up with funny looking factors that are probably opposites of whatever they mention, like they say 2, I do a minus 2, you know. So that when I plug in the number they're talking about, it makes a 0. So now I have x minus 2, and that means if I plug in a 2, then that makes a 0, because 2 minus 2 makes 0. That works out well. When they say multiplicity 2, that just means there's two factors like that. That's all. X minus 2 times another x minus 2. Now I have multiplicity 2 of this because there's 2 of it, you know? And there's also multiplicity 2 of this other one at x equals 0, so we're going to do the same thing. You could do x minus 0 if you like, x minus 0. Although minus 0 is kind of dumb, so you just as well just not put the minus 0 because it doesn't take anything away. But whatever, you could put that if you like. Anyway, it's just x and x, or x minus 0 twice. But it's multiplicity 2, so there's 2 of it. One of them there, and then another one. And then the only other thing it says is that we have a root of multiplicity 1 at x equals negative 2. So we got to figure out how to write a factor so that when I plug in a negative 2, it gives me 0. And it's only a multiplicity of 1, so there's only one of it, is what they're saying. And so there's one of it. We'll only need to make up one of them, which is good for us because at this point we already have 4 factors, and we only have a 5th degree polynomial, so here comes the number 5. And now to make it so that negative 2 is a root, we're going to do probably what you would figure, and so we'll say, well, we'll do a x plus 2, so that when we put a negative 2 in, negative 2 plus 2 makes a 0 there. And that'll be good. From there, don't worry about having to FOIL it out. We'll just clean it up a little bit. On these ones where we had x minus 0 and we didn't bother to put the 0, you just as well just call those x times x. And so that simplifies a little bit because x times x we could call x squared pretty quickly. But I wouldn't bother to FOIL anything else out. And we'll just say this is x minus 2. Well, I guess there's 2 of that. So we could mention that and say x minus 2, there's 2 of that. So x squared is x times x. X minus 2 twice is x minus 2 twice, or squared. And then there's an x plus 2. That condensed it a little bit because then we don't need this last part. So we have x minus 2, x minus 2 twice, we have x twice, and we have an x plus 2. And now it's the 5th degree polynomial they were talking about because there's 1, 2, 3, 4, 5 factors. Looking good. And it has that coefficient of 1, remember. Leading coefficient of 1 means, again, I don't need to worry about putting a number in front of my x squared. I can just assume that it was just a 1x squared. Now there's another one here. Number 8, it starts getting the same kind of thing, but it starts getting a little bit funkier here. Let's see what we can do. Okay, so number 8, polynomials degree 4, so there's 4 factors. We'll do that, and we have the multiplicity of this and that, so that's no big deal. Let's set all that up. And then notice the difference here is they give a little bit more information here. Instead of saying the coefficient is this, they say it goes through the point 5, 252. So let's talk about that in a second, but for right now, let's go ahead and set up this polynomial of degree 4. We have a root multiplicity 2 at x equals 2 again, so that'll be very similar to the last one, p of x. X equals 2 is the root, so I'm going to put x minus 2 so that when I put in a positive 2, it's 0. That's good. And there's multiplicity 2 of that, so I did 2 of it. Now, multiplicity 1, I have x equals 0 is one of them. Oh, there you go. X equals 0 has a multiplicity 1, so we'll do x minus 0, or just x. And then also at x equals -2. That was part of the multiplicity one as well. So x equals -2. That's going to do an x plus 2. Very much like the last problem so far. Here's the only thing. In this situation, they also say beyond all that information, it goes through the point 5, 252. And what that means for us, guys, is the 5, as you guys know, is an x, and then the 252 is the y or the function value or whatever. And so x, I'm going to put y here, even though we're talking about p of x, but whatever. And to emphasize, okay, not only is this x, that's the number you put in for x, and this is the number you get out when you put the x in. So 5 is the number you would put in for x, and you would expect to get 252 for an answer when you do that, is what they're saying. So what we could suggest here is then, if we have our function just right now, and if we didn't need to do anything extra to it to make it match up, then we would have this reality that if I plug in a 5 everywhere I see an x here, then the answer should be 252. And if when I plug in 5, if the answer is not 252, then I don't know, we'll have to adjust somehow, And so let's look at that real quick. We try. Let's see. Try. Okay, we try. We're going to plug in a 5 here everywhere we see an x, and we're going to see question mark, is that going to equal 252? Question mark. Is this all going to equal 252? Let's see. And if not, then we'll adjust it somehow, So we'll plug in the 5. 5 minus 2 is whatever that is, 3 or something. And then put in another 5 there. So 5 minus 2 again, 5 minus 2. And then x again, so I'll put a 5. And then we have 5 in place of this x is 5 plus 2. So whatever that is, 7. 5 plus 2. And then we'll just see where that leads us. 5 minus 2 is 3 times another 3 there. And then times 5, and then times 7, I guess. And we're like, question mark, did that equal what I wanted it to? What is that going to equal? Let's see here. This is 3 times 3 is 9. 9 times 5 is 45. 45 times 7. Let me think about that one for a second. It's here. 40 times 7 is 280. And then 5 times 7 is 35, so then that's going to be a 5, 11, 315, I guess, which is unfortunate because that means this is a no. This 3 times 3 times 5 times 7, that makes 315, not 252, and so we got to somehow figure this out. And so here's a homegrown version of this. What this essentially means is we're going to have to times or divide this mess by something to make it 252. Because right now it equals 315. Does not equal 252. You don't want to leave it there because that's not actually an equation. So what I would suggest is, guys, here's the dirty trick. Check this out. We'll say 315, and I'm going to adjust this function now. I got to figure out what it is that I need to, I know I have all the roots right. I just got to figure out what to times them by or divide them by so that when I'm done, it won't equal 315 anymore. It'll equal 252. So what I do is we'll say all this stuff really made 315. So let's say, well, what if I said, okay, 315 times some number I'm going to use, I'll put an A, some number that I'm going to use to times by this 315. We'll end up making it equal to 252. So 315 times something makes 252. Let's see if we can figure that out. But if you're lazy, you'll just do it the algebra way. So we'll just divide the 315. And then we got A sitting here. That's the number that we're going to have to use to adjust our function later on. Equals whatever 252 over 315 is, which is a nasty old fraction. Pretend like you can read what I'm writing here. Anyway, 252 over 315, that's a nasty fraction, and you could just leave it like that, but it does actually happen to reduce in this case. 252 over 315, by the time you reduce it, I think like you could take 9 out of both and then some other stuff. Ends up being 4 out of 5 if you reduce it, or you could make it 0.8 as a decimal if you like. That's the A number that we're going to have to use to adjust our function. So the way that works for us, since this is a quick take, all we're going to have to do is we'll say we had that polynomial function like they described, x minus 2 a couple of times, and an x plus 2. All I got to do is squeeze my a number, that coefficient, what is it, 4/5? Yeah, it's right in front here. And so right now I'm going to give you a clean version of all this. We'll write this new polynomial function right over yonder. We'll say p of x equals, and then it's all going to be just like we put. There's no way I have room to put it there. What was I thinking? We'll put it upstairs here. Okay. Say p of x equals, and then leave a space here because we got to put our number, but it's still x minus 2 twice, and I'll go ahead and put squared. And then times x, you can put a little times dot if you want, or you could put the x in front, whatever you want to do. And then times x plus 2, there's one of those in there. And then you could put times dots everywhere, however you want to write this. But then remember, we have to times it by that special number, and so we'll put 4/5 here in front. Or you could put 0.8 if you like. It looks like I was looking at the answers, and they got 0.8 because that's the decimal version of this. That would work too. So then I guess that's as far as it'll need to go. Ta-da! I want to put the x in front. I don't know, whatever, it doesn't really matter. Anyway, that's the idea. You put the roots down, then you got to figure out what the special number is to make it all work the way you need it to. Kind of an intense process, Similar idea with number 9. The only thing is they're going to tell you all the roots, and then they just tell you that the y-intercept is y equals 16. And that's important to know because it works in the same way. Remember I won't do this whole thing with you, but when they say the y-intercept is whatever, remember, that's a point, just like, 5, 252 is a point? This is a point as well. Y-intercept is a point because the y-intercept is a 0 for the x part every time. That's what a y-intercept is. It has a 0 on the x part. And then the y part is whatever they say. So this one you'll handle similarly. You do the whole p of x thing with all the roots, and then you just make sure that it goes through this point so that when you plug in a 0 into every x, the answer is supposed to be negative 16. And then it'll handle just like the other one did. Similar idea here. This one's from a picture, so I at least wanted to get you guys going in a good direction. For numbers 10 and 11, we have this idea of, they say, write the equation for a polynomial like this. Not super easy to do at first, but if you've been through a few of these, it ends up okay. So we have x-intercepts at -4, -3, 2, and 4. What looks like x-intercepts are also going to be roots or zeros or however you want to call these things. And so roots of the polynomial are going to be at these places. So just pretend like they gave it to you in words. We have a root at -4, a root at -3, one of them at 2, and one of them at 4, and we just got to make a polynomial that fits that. And then we got to make sure we get our leading coefficient right, the part you got to times to adjust it, and that's where this guy's going to come in. We have one dot that's given that we know that's not one of these roots, and so we'll focus in on that. This is a y-intercept like on number 9, and the coordinates of that thing are, we plug in a 0 for the x, and then y part is -3, so we're going to have to make sure that 0, -3 works for our in and our out. And so that'll work out in a second. For right now, let's go ahead and get that polynomial working. So if -4 is a root, then we'll say I'm going to put x plus 4 so that -4 zeros it. And then the same thing with -3. We'll do x plus 3. And then we have x, since this is a 2, we'll do x take away 2. So that 2 minus 2 is 0. And then 4, the same way we'll do it. That's a positive 4, so we'll put x minus 4. Then we have all this stuff. That's our new polynomial function. You can do y equals that, or p of x equals that, or however you want to do that. But then we got to figure out what the heck number to times in front of it to make sure that it's not just something that has roots there, but it's exactly this polynomial. And so we know that with something, we know, what do we know? We know this. We know that if we plug in an x of 0, then we get a y output of -3, and so we'll just check that out. If we plug in zeros here, we'll make sure we get an output of 3, -3. Let's try that real quick. If I plugged in a 0 here, 0 plus 4 is 4. 0 plus 3 is 3. 0 minus 2 is negative 2. I like plugging in 0. 0 minus 4 is negative 4. And I'm wondering, question mark, is that going to already by itself equal negative 3, or do we have to adjust it, you know? That's supposed to be a question mark. I don't think this is going to equal negative 3. Look at all that. It's huge. And so, let's see here. 4 times 3 times negative 2 times negative 4. The negatives will cancel, so whatever about that. But this is 2 times 3 times 4. That is 24 times another 4. That's like 48 times 2, so 96, I guess. So we're like, this is 96, not negative 3. So don't exactly need the question mark anymore. It's basically just a no. But what we can do is we'll say, well, it's 96. It's not 3 like it's supposed to be negative. And we'll just do that mystery thing. We'll put an A here, and we'll say 96 times something is supposed to give me negative 3. How do I figure that out, you know? And then we'll just divide it like we do. Boom. Divide the 96, divide the 96, and now we have our A term. Will be whatever the heck negative 3 over 96 is. It reduces down a little bit. That's negative 1 out of 32. And that'll be the A term that you were looking for. And so we'll say, oh, that's a perfect term, so that when I plug in zeros into all this, if I times it by, you know, my answer by negative 1 out of 32, then it'll cancel down, and it won't equal 96 anymore. It'll equal negative 3, like it's supposed to. Anyway, so that's my quick take on that. Okay, what else we got? We got this one. I paused it for a second, so maybe this jumped in the way. I don't know. But we have find all the zeros of the function. F of x equals all this mess. Into the zeros separated by commas. Oh, you couldn't read all that. Look at all that. Amusing. This is somehow supposed to be the answer I get on my version of the question. But the idea is we're supposed to figure out all the zeros here. Or in other words, what are all the x values that I could plug in that would make this thing equal 0? And we know that this is an x to the third equation, so we're looking to get as many as like 3 different answers here. You know, and so that'll be a little bit interesting. Not easily done. And so I wanted to talk to you guys about this. We don't have like, once you get to higher enough equations, you know, higher enough powered polynomials, we don't really have good strategies like the quadratic formula for everything.